Okay. Hello, dear colleagues. Today at our dissertation council, we have the defense of the dissertation work of Dinara Amankulova, titled Development of a Method for the Non-Catalytic Synthesis of Meta-aryloxyphenols from 1,3-cyclohexanedione, submitted for the PhD degree on the educational program 8D07105, Chemical Technology of Organic Substances. The dissertation work was performed at the Department of Chemistry and Technology of Organic Substances, Natural Compounds and Polymers of the Faculty of Chemistry and Chemical Technology of Al-Farabi Kazakh National University, and on the basis of the laboratory of University of Alberta, Edmonton, Canada. Scientific supervisors: Moldyra Kimzhanovna Dusibayeva, candidate of Chemical Sciences, Associate Professor of the Department of Chemistry and Technology of Organic Substances, Natural Compounds and Polymers of Al-Farabi Kazakh National University. And Derek L.J. Clive, PhD, Doctor of Science, Professor of the Department of Sciences and of the University of Alberta, Edmonton, Canada. So foreign supervisor, I think he is not present, but you have the review. Yes? Okay, official reviewers: Justin Moore, PhD, Associate Professor of Chemistry, University of Illinois, Chicago, United States. Tuligen Muratovich Seilkhanov, Candidate of Chemical Science, Professor of Kokshetau State University, Head of the Laboratory of Engineering Profile of Nuclear Magnetic Resonance Spectroscopy, Kokshetau, Kazakhstan. Official reviewers are present. So temporary members of the Dissertation Council: Serik Drahmetovich Fazilov, Academician of the National Academy of Sciences of Kazakhstan, Doctor of Chemical Science, Professor at the Institute of Organic Synthesis and Coal Chemistry of the Republic of Kazakhstan. Kumarswamy Reddy Nandarapu, PhD, Faculty Inspire at the Indian Institute of Technology, Tirupati, India. Khadichahan Sabirjanovna Rafikova, PhD, Associate Professor of Satpayev University, Almaty, Kazakhstan. And Meiranbek Alibekovich Aspanov, PhD, postdoc at the National Center for Natural Products Research, School of Pharmacy, University of Mississippi, United States of America. So as I see, all temporary members are also present, so we can continue our defense. So please keep your web cameras on during the defense. The defense is recorded and broadcasted on YouTube channel of the university. I remind you that our dissertation council should make one of 4 decisions: award the PhD degree, send the dissertation for revision, send the dissertation for another defense, and refuse to award the PhD degree. Yeah, so in the end of our defense, we will have to vote for one of the decisions. So now we have the speech of the scientific secretary, then the speech of the doctoral candidate, then questions, reports of scientific supervisors, official reviewers, yeah, and then just discussion and voting, secret poll. Okay, so now the floor is given to the scientific secretary, Professor Sagdat Medyabekovna Tajibbayeva, for presenting the documents available in the personal file of the applicant. So please.
Thank you, Amankulova Dinara, born in 1994. In 2015, she graduated from Al-Farabi Kazakh National University, Al-Farabi Kazakh National University, with a Bachelor of Techniques and Technologies degree. Then from 2015 to 2017, she studied as a master's student in the Department of Chemistry and Technology of Organic Substances, Natural Compounds, and Polymers. From September 2020 to June 2023, Amankulova Dinara studied in the PhD doctoral program of the Faculty of Chemistry and Chemical Technology of Al-Farabi Kazakh National University. The topic of the dissertation, research, and scientific advisors were approved at the meeting of the Academic Council of the Faculty on 26 October 2020, protocol number 2. In the personal file of Amankulova Dinara, there are copies of bachelor's and master's diplomas, a list and copies of publications, positive reviews of scientific supervisors, protocol of the enlarged meeting, and all other documents in accordance with the regulations of Committee for Quality Assurance of Education and Science of the Ministry of Science and Higher Education of the Republic of Kazakhstan. The main research results on the topic of the dissertation are presented in 3 published works, including 1 article in an international journal with a percentile of 60, quartile 2, and 1 review article in an international journal with a percentile of 83, quartile 2, and the abstract included in the international conference proceeding. On May 5th of 2023, the work of Amankulova Dinara was discussed at an enlarged meeting of the Department of Chemistry and Chemical Technology of Organic Substances, Natural Compounds, and Polymers of the Faculty of Chemistry and Chemical Technology of Al-Farabi Kazakh National University. The meeting was attended by 30 people, and the first reviewer, Kayukova Lyudmila Alexandrovna, Doctor of Chemical Sciences, Professor, Chief Researcher of Bekturov Institute of Chemical Sciences, in her positive review indicated 18 comments, mostly with editorial character. And the second reviewer, Mukanova Miruer Tisembekovna, candidate of Chemical Sciences, Senior Lecturer of the Department of Chemistry and Technology of Organic Substances, Natural Compounds, and Polymers, also gave a positive review indicating 3 comments. All the asked questions and comments of the reviewers received answers. Therefore, the scientific seminar unanimously recommended the work for the defense. Extract from protocol number 15, dated May 5th, 2023, was approved by the Vice Rector of the for Social Development, Aidosov Nurjan Sarsimbekovich. And the date of defense, official reviewers and temporary members of the Dissertation Council were appointed on October 10th of 2023, protocol number 30, at the meeting of the Dissertation Council.
Okay, thank you, Professor Tajibayeva. Do you have any questions to Scientific Secretary? Okay, if there are no questions, then we can proceed. And the screen is given to the PhD candidate, Dinara Erkinovna Amankulova. So the time is 20 minutes for your talk.
Do you see my screen?
Yes.
Dear committee, my dissertation work named Development of a Method for the Non-Catalytic Synthesis of Meta-Aryloxyphenols from 1,3-cyclohexanediol. The purpose of the dissertation research to develop an efficient and novel method for the synthesis of meta-aryloxyphenols from 1,3-cyclohexanedione. The following tasks were set up to achieve our goals: conduct research on the conditions of obtaining 3-aryloxyphenols, analyze structural characterization of synthesized compounds, and present technological schemes for the developed methods for synthesizing intermediate and final compounds, and calculate the material balance of the production. We submitted 3 main provisions of the dissertation for the defense: a novel approach for synthesizing meta-aryloxyphenols via cyclohexane 1,3-dione has been devised, compromising a 4-step synthesis protocol. The method avoids the need for operations to bypass the ortho and para directing effect of oxygen, resulting in a simplified and streamlined synthesis process. The synthesis method doesn't entail the use of heavy metals or ligands, making it more ecologically sound. Synthesis of 3-chlorocyclohexanone. 3-chlorocyclohexanone was obtained with 83% yield using oxalyl chloride and dimethylformamide in dichloromethane. The reaction proceeds through a multi-step mechanism, which is shown in this slide. The process begins with DMF activating oxalyl chloride, creating a Wills-Meyer reagent. A charge-separated species forms, leading to bond ruptures and new bond formations. A collapse reaction occurs, eliminating chloride as a chloride. The chlorine species then attacks the carbon, creating a neutral intermediate. This intermediate experiences an elimination reaction with bond ruptures, yielding carbon oxide gases. The final product is a chloride salt intermediate, which means a Wills-Meyer reagent. At the same time, the protonation of the lone pair of the carbonyl group on 1,3-cyclohexanedione by a hydrogen ion generates the enol tautomer. Upon reacting with the Wills-Meyer reagent, 3-hydroxycyclohexanone produces 3-chlorocyclohexanone, which regenerates DMF and forms HCl. During this process, the oxygen atom of the hydroxyl group attacks the carbon of the Wills-Meyer reagent, and the electron forms from the p bond placed onto the nitrogen. Furthermore, the chloride ion attacks the beta carbon. Subsequently, beta elimination takes place and breaking CO bond and forming 3-chlorocyclohexanone. Synthesis and bromination of 3-aryloxycyclohexanone. The nucleophilic substitution reaction of phenol derivatives with 3-chlorocyclohexanone under refluxing acetone conditions in the presence of potassium carbonates represents an efficient method for the synthesis of meta-substituted cyclohexanones. The reaction mechanism can be summarized as follows. The potassium carbonate in the presence of acetone deprotonates the phenol derivatives to form the aryloxide ion. This acts as a nucleophile and attacks the electrophilic carbon of the 3-chlorocyclohexanone, resulting in the formation of a new carbon-oxygen bond and forming an enolate. Then enolate cationizes with explosion of chloride. Then obtained 3-aryloxycyclohexanone undergoes two bromination reaction with N-bromosuccinimide in DMF. The transfer of lone pair of electrons from the oxygen of the aryloxy group of compound 3 to the beta carbon results in the breaking of the p bond and the formation of a new bond between the bromine atom from MBS and the second carbon. The negatively charged succinimide ion generated during the reaction deprotonates the second carbon of the cyclohexanone ring, which leads to the formation of two bromo 3-aryloxy cyclohexanone. The introduction of a bromine atom on the second carbon of 3-hydroxycyclohexanone prior to the aromatization reaction, because it allows the protonation from the fourth carbon, and also the bromine atom serves as an effective leaving group in the aromatization reaction. Initially, the bromination of 3-hydroxycyclohexanone at second carbon position proved to be challenging until the discovery that NBS in DMF at 0 degree followed by warming to room temperature gave the required 2 bromo derivatives efficiently. Freshly recrystallized NBS from the water was used as a matter of routine. In this slide, we can see all synthesized brominated compounds with reaction conditions and yields. As you noticed, we obtained compounds 3 with more than 80% yield, except compounds 3D, E, and H, reasons of which I will explain next. The effect of placing substances with higher exert steric hindrance. Our initial attempt at synthesizing 3D and 3E involved a universal approach. However, we got a low yield of product when using acetone as a solvent. To improve the yield, we tried using solvents with higher boiling points, such as butanol and DMF. First, we attempt with using acetone as a solvent at 60 degrees for more than 40 hours, and then we got 6.5% of compound 3D and 21% of compound 3E. With butanol at 75 degrees, we got 23% of compound 3D. And finally, with DMF at 100 degrees for 24 hours, we got 52 and 48% of yield of compound 3D and 3E. Using DMF helped to increase the yield and decrease the reaction time. When we used one equivalent of 3-chlorocyclohexanone and one equivalent of hydroquinone and 2 equivalent of potassium carbonate in refluxing acetone for 21 hours, we got 69% of 3,4-hydroxyphenoxycyclohexanone, compound 3I, and 13% of compound 3H. And we cannot continue synthesis of 4-hydroxyphenoxycyclohexanone because of ability of the hydroxyl group to react with bromine in the next step. Therefore, we worked on increasing the yield of compound 3H. Increasing the amount of potassium carbonate to 4 equivalents and the refluxing in acetone for 43 hours gave us 71% of pure compound 3H. The yield of the reaction can improve by increasing the concentration of the mild-based potassium carbonate used to facilitate the nucleophilic attack of hydroquinone on 3-chlorocyclohexanone, and an increase in potassium carbonate from 2 to 4 equivalents leads to higher base concentration, which improves the efficiency of the protonation of hydroquinone and makes the nucleophilic attack more efficient. In this slide, we can see all carbon NMR for compounds 3 and 4, and as you can see, the chemical shapes of the second carbons were changed from doublets to singlets, which shows that bromination was perceived effectively. And in a proton NMR data, we can also see that signals of proton adjacent to the second carbon were disappeared, which also showed successful bromination. In the course of our investigation, we successfully synthesized meta-aryloxyphenols by utilizing 2-bromo-3-aryloxycyclohexanone and 1,8-diisobicyclo and undecane in a toluene. The reaction was conducted under ambient atmospheric conditions at a room temperature. The reaction mechanisms for the synthesis of meta-aryloxyphenols can be explained as follows. DBU as a strong base, the protonase force carbon in compound 4, which leads to resonance stabilized enolate anion. The enolate anion undergoes an intramolecular elimination reaction facilitated by the electron-rich oxygen atom and the positively charged protonate DBU. This results in the protonation at the second carbon. The second equivalent of DBU, the protonase fixed carbon on the cyclic compound that leads to releasing a bromide as a leaving group. The resulting intermediate undergoes to ketoenol tautomerization to form the final meta-aryloxyphenol product. To optimize aromatization reaction, we explored various bases and solvents as detailed in following table with phenoxybromoketon. Experiments were conducted with DBU in solvents such as acetonitrile, toluene, ethanol, DMSO. And under both room temperature and boiling point reflux condition. Reflux reaction using DBN in acetonitrile for 48 hours yielded 43% of desired product with impurities present. When employing sodium acetate in ethanol, we initially observed no significant change on thin layer chromatography after 2 days at room temperature. However, following 2 days of reflux, we got 36% yield, and after 3 days, yield was increased up to 57%. Utilizing sodium carbonate under reflux for 2 days resulted in a 30% yield. A reaction involving DP in acetonitrile under reflux for 68 hours produced 46% yield of DP. We also experimented with sodium phenoxide alone in acetonitrile, DMF, and tetrahydrofuran under reflux for approximately 40 hours. This reaction led to 38, 28, and 66% yields of purified desired product. Lastly, the combination of DBU and the sodium phenoxide in acetonitrile yielded a 40% mixture of DP and the phenol. As shown in the table, we got the best result using DBU in toluene at room temperature. In this slide is shown all synthesized meta-aryloxyphenols with reaction conditions and the yields. We obtained different range of yields because of nature of substituent aromatic compounds. With electron withdrawing groups, for which we employed 4-iodophenol, 4-chlorophenol, and methyl 4-hydroxybenzoate, the aromatization shows lower yields than other meta-aryloxyphenols. In that case, treating with DBU in acetonitrile resulted in the formation of both the desired products and approximately of 4-iodophenol, 4-chlorophenol, and the methyl 4-hydroxybenzoate determined by proton NMR, which was present in the starting bromides. In the current experiments, a competing reaction is observed. Theoretically, the release of initial phenol might transpire through an addition elimination mechanism. Based on these findings, we hypothesize that the bromide ion trace amount of water can exhibit nucleophilic behavior toward a third carbon of the bromoions in the presence of DBU in acetonitrile or DBU itself. However, the dehydrobromination pathway, which results in aromatization, is particularly dominant for less acidic phenols. As we know, DBU is frequently employed as a non-nucleophilic base. Its nucleophilic properties are, in fact, well established. here is the data of carbon and the proton NMR, and we can see that all aliphatic signals were disappeared. Our approach for the preparation of methylhydroxyphenols has been successfully developed and offers a gentle alternative to the classical Ullmann reaction. This development presents a universal method for synthesizing methylhydroxyphenols from cost-effective and easily obtainable starting materials. The procedure involves a series of steps, including the synthesis of starting material, the nucleophile substitution reaction, and bramination, and the final aromatization step. In the following slides are shown all synthesized compounds and the reaction conditions. We used a number of different phenols in which the aromatic ring carried various substituents so as to explore the outcome with electron donating groups and electron withdrawing groups, as well as the effect of placing substituents in a position to exert steric hindrance. As we can see, the aromatization works best if the allyloxy unit carries an electron donating substituent. With electron withdrawing groups, for which we employed 4-iodophenol, 4-chlorophenol, and 4-methyl-4-hydroxybenzoate, formation and bramination of allyloxy ketones work well. However, the aromatization of them shows lower yields than other methylhydroxyphenols. And the aromatization takes place even when substituents methoxy and the tertiary butyl are present ortho to the hydroxyl of the starting phenol. We choose to let the aromatization reaction proceed for more than 24 hours without strict time constraints. And however, we observed through TLC monitoring that the aromatization of the 2,6-dimethoxy compound and the 2-tertiary butyl compound occurred at a slower rate. It's possible that in this instance, the aromatic substance obstructs the base's access to the fourth carbon hydrogens in the compounds. And we propose technological schemes detailing the developed methods for synthesizing intermediate and final compounds. And additionally, material balance of production were calculated to assess the efficiency of the synthesis processes. Conclusion, and developed an efficient and novel non-catalytic method for the synthesis of methylhydroxyphenols from 1,3-cyclohexanedione. The research conducted on the conditions for the synthesis of 3-hydroxycyclohexanone by nucleophile substitution reaction is the introduction of directing group by bramination of second carbon, and the synthesis of methylhydroxyphenol by aromatization. The structural characterization of the synthesized compounds using various analytical techniques and the presentation of technological schemes for the synthesis process and material balance of production further demonstrate the completeness of the solution of the tasks outlined in the dissertation work. During the research, 2 articles were published, including one article in the journal Tetrahedron and another article in the journal Molecules. Additionally, the findings of this research have been presented and discussed in international conference Al-Farabi Alama 2023. I appreciate for the support and help in this research to Professor Derek Clive, Associate Professor Mulder Dusebaeva, all co-authors, Dr. Arava Amarandaretti, Tayo Akiyodon, University of Alberta, all the faculty, technical and non-technical staff members of Department of Chemistry and Chemical Technology, Al-Farabi Kazakh National University and the University of Alberta, below 12 members. Thank you for your attention.
Okay, thank you. So now we have time for questions. So if you have questions, just raise your hand using Zoom feature reaction For example, or you can just raise your hand and I can see you. And who has questions? Colleagues, dear colleagues. Okay, Professor Bukitbayev.
So Dinara, thank you so much. You have demonstrated really very flexible skills in synthesis of organic compounds. And I didn't remember as a researcher like yours, because you're organic who synthesized. But as I know, in that synthesized organic compounds fields, many researchers deal with searching the catalytic systems, because catalytic systems, it cut the stage of synthesis, because you have proposed 4 stage. It is so long, it seems to me. And why did you think that the using as a catalysis will make impact for the quality of final compound? Because catalytic systems do not included, really, didn't be included for the final compound.
Okay,
This is my
thank you.
question. Yeah.
Thank you for the question. First of all, we all researchers on the catalytic synthesis, we usually use palladium catalysts or copper catalysts, and as we know, they are, especially palladium catalysts, so expensive, and in that case, our investigation is more cheaper than using catalysts. And in second question, secondly, and it's we think it's a more ecological safer, because we don't have that metallic traces after the reactions. And also we can assume that maybe in the final compounds, maybe it's maybe possible that we having the traces of catalyst, metal catalyst.
And then the second small question. Did you compare the rate of reactions or yield of the final compound in catalytic way and yours without catalytic?
We mean you mean cost of reactions?
Not cost, the rate of or maybe yield of the final product using the catalytic system and the non-catalytic system, and how long you need to produce the same quality using first way and the yours way.
As I remember, using for example, for the 3-phenoxyphenol, they synthesized 70%. If I am right, 70% yield, and we synthesized 83% yield. And about time, I am not sure exactly.
Time for synthesis organic compounds, time is very important.
Yeah.
You know about that. So thank you so much.
Sure.
Okay, other questions? Okay, Dr. Ospanov, please.
Hi, dear colleagues. I have one question. Is there any activity
Thank you for the question. We didn't check the activity, biological activity of the compounds, because our work based on the synthesizing and developing new method of synthesizing meta-hydroxyphenols. But from the literature, yes, meta-hydroxyphenols have anti-inflammatory, antibacterial activities.
Thank you. And there's one more question.
Yes, please.
You said in the slides that about CNMI, and you said it's doublet. Can you explain more about this one?
Oh, yes, just.
I don't remember which side, but
Yeah.
yeah, maybe the
No.
previous one.
Yeah.
Yes,
Yeah,
this
it's doublets. Yeah. And singlets, doublets or singles based on how much protons carbon this carbon carries. And here we can see that we have one proton, and it will be a doublet. And when carbon doesn't carry any proton, it's a singlet.
Yes, you mean doublet, and you are showing the carbon, and carbon is not how to say. Yes, you are saying about proton, but you are describing here carbon.
Yes.
Yes.
Oh,
Yes.
yeah, sorry. It's in the carbon NMR. We also can see that peaks are double. Peaks are usually came
You mean
as
double?
doublets and singlets, doublets, triplets, and quartets, and up and down here. And we can calculate the number of protons and find out if it's a doublet, singlet, or triplet.
It may be double intensity, but it cannot
Oh,
be.
yeah. Sorry, yeah. I mixed out.
Okay, thank you.
Thank you.
Okay, thank you. Dr. Kumaraswamy, ready, please?
Thank you. So, yeah, Dinara, thank you. Your presentation was excellent. And yeah, you are very smart in presentations, it seems. So, yeah, I have gone through your thesis. The way of your writing was very good. And then, yeah, there are some of the mistakes I found that the Kimdra structure sheet should be consistent, but it was like, it's not in the format. Like, make it like consistent when you are submitting final thesis. Okay, that's what I found a mistake. So then, can you go to the presentation if possible, slide number 6? So I have some inquiries. It's not a okay.
Yeah.
Yeah. Here you are talking about making from chloro to aryl alcohol, right?
Yeah.
So from 2 to 3 in the presence of aryl alcohol with potassium carbonate acetate condition. So have you tried any time with the sodium phenoxide instead of aryl alcohol? Sodium phenoxide.
In this case, not. We didn't use sodium phenoxide. We tried to use sodium phenoxide in the final aromatization step.
Exactly, but why can't you try here? Because I don't know what was the reason you directly used phenolic aryl alcohol, because that is also more reactive than this, right?
Oh, yeah. We already got a good yield, so we didn't try it.
So,
yeah.
One more, the same question, same reaction. I wanted to ask you one question. Instead of aryl alcohols, have you tried any time like tetrabutanol or methanol to trap, just like only chlorine, chlorine is replaced with methanol or methoxy or tetrabutyl alcohol, or something going to happen? So have you tried that reaction?
To obtain aliphatic substitute?
Yes, exactly. Whether aliphatic is sufficient or something may happen. That's what I wanted to.
In this investigation, we didn't try it because that work's already done in the Professor Clive's work group.
Okay. Thank you. So one more query on slide number 9.
9.
Yeah. Here in the entry 2, you mentioned like, compound 3H only 21% of yield. What happened the remaining compound? Like, you recovered the starting material, or compound may be decomposed. What happened here?
Oh, yeah. First, we got 13%, and with 1% fluorocyclic hexanon. As we can see that we in the structure, it's two molecules of cyclic hexanon, and here I think one equivalent it wasn't enough to produce, and when we increase the for 3 fluorocyclic hexanon up to 2, we got 21%, and when we increase and also potassium carbonate, we increase the yield up to 70%.
Yeah, but the middle one, 21% only you got 3H, right? What about the remaining compound? Yeah.
Oh yeah, sorry.
Decompose.
Yeah, we didn't calculate it because it's not. We didn't use.
Okay. Thank you. It was very nice presentation.
Thank
I
you.
enjoyed it. Thank you.
Thank you. Dr. Rafikova, please.
Good day, dear colleagues. Thank you very much, Dinara, for your presentation. I have a quick question. So, can you tell us about social economical impact of your research? And what can you say about large-scale production of your synthesized products? And about, yes, large scale, I said. Yes, in terms of energy, safe energy. As you see, you need long time to synthesize. And if you compare synthesis of your compounds by using catalysts, what can you say? And why did you use only NMR analysis?
Okay, yeah. Thank you. First, it's about economical. About economics. Our of only one reaction of 4 steps requires a high temperature. It's 60 degree, and the other 3 reactions goes under atmospheric under room temperature. And I don't think that it requires so much energy, and we didn't compare on that economical stage with catalytic methods. We just developed another way to synthesize meta-aryloxyphenols. And about the spectrometry, we used to analyze our compounds, IR spectroscopy, mass spectroscopy, and 2 NMR spectroscopies.
So any literature about production by using catalysts, just to compare any theoretical data? You don't have this, yeah?
No, we don't have.
Okay, thank you. Thank you very much.
Thank you.
Thank you. Other questions? Okay, so I have questions. So in from your slides, I see the yields. So you report the yields. My question is, how did you calculate these yields?
By the comparing with theoretical yields by calculation, just as using theoretical yield as a 100% and obtained yield as unknown %.
Which means isolated yields?
Yes, isolated yields.
Okay.
Okay, but so you get the final product. Yeah. So after this, what exactly did you do with this final product to analyze the concentrations of all compounds which are present in the final product?
After purification of the compound.
After synthesis, I mean. Or after synthesis, you purified the compound, yeah?
Yes, yeah, we worked out, and after that we purified compounds, evaporated them, and after that we measured the mass of the compounds obtained.
Okay.
And after measuring, we analyzed to the mass NMR spectroscopy. if we see that NMR spectroscopy is a good proton NMR, we obtain to get carbon spectroscopy.
What do you mean good NMR spectrum? What's
Without
in-
without impurities. Usually we use proton spectroscopy to see if any impurities in the product.
Yeah, but NMR spectroscopy is not developed, is not designed to determine impurities, you know, because you can have the compounds with similar bonds and functional groups in impurities, and they can overlap. So for determination of the purity, so typically, like the methods like chromatography, for example, gas or liquid chromatography, are used,
Yeah.
or maybe, or I see in your dissertation that you use mass spectrometry.
Yeah.
Yeah, but I don't see the results, unfortunately, of the mass spectrometry. And I have a question: why you didn't use the chromatography, HPLC, for example, or GC or GCMS?
Yes, because they were not available, and we after each reaction we used TLC, thin layer chromatography, to see if reaction proceeds, and we purified them with chromatography, column chromatography.
Yeah, but this method is completely inefficient compared to, let's say, HPLC or GC. So number of theoretical plates is much lower. So separation power is very low compared to HPLC or GC, for example. So you say that they are not available. They are not available where?
For us in the university, at the university.
No, we have many GC, we have many HPLC instruments. We have a lot of them. Why you didn't use them?
I think with all of we used 4 methods, and if we combine all of these methods, we can justify purity of the compounds.
No, you can never do that. It was possible like 50 years ago, but not now. Now these analyses are required to justify the purity. Yeah, and it's not that difficult to do them. But okay, but you use mass spectrometry, okay? But somewhere in your dissertation, I don't see any mass spectra.
Yes, because of size of my dissertation, we decided to not include the mass spectras.
No, but you have a lot of space for NMR spectra. Yeah, but some way you don't include the mass spectra, which are like more important than NMR spectra for purity, especially. So because from this mass spectra, you can really see the impurity of your compounds, but some way I don't see it.
Okay.
But okay, even if you don't provide it, then can you just discuss this mass spectra, how they were, what was present on this mass spectra, what compounds, what peaks? I see some results in the tables, you know,
Yeah.
in your
In the
dissertation.
thesis, yeah. Calculated mass and obtained mass of the compounds.
Yeah, okay. But, for example, table 2.2. So mass spectrum data for compounds 3A to 3H. Yeah, so I see only, how to say, these are data for different compounds or what?
Yeah, it's data for different compounds.
Yeah, but okay, but what was present on this mass spectra? So maybe I can just show this thesis. Yeah, okay. Do you see this table on the screen? Okay, so I see the results, yeah, the mass spectra description, let's say, in this table. So it means you collected like 8 different mass spectra. And what was exactly present on this mass spectra?
Here is we obtained we synthesized 8 compounds, and for each it's a formula of the compounds and the calculated mass of the compounds, and as we can see, calculated mass and founded mass are same with little differences only. But we don't we don't search.
What was exactly present on your mass spectra? For example, let's say for compound 3B, what was present on this mass spectra? Do you remember?
Not exactly.
Okay, but how did you calculate this value from the mass spectra? The calculated
Molecular mass.
How did you calculate? How did you find it from mass spectra?
We used data. It's some kind of app for the calculation as a ChemDraw, but different. We draw our structures and they calculated mass of the structures.
No, but how this mass spectra? So you have mass spectra, yeah. So what is present on this mass spectrum?
Just spectra with peak on this amount of found mass.
Okay, the peak with this mass.
Yeah.
Okay, but what type of mass spectrometer did you use? Display ionization mass spectrum.
Yes, it's 2 types of ionization techniques. We use electron ionization and the electrospray ionization, which means that electron ionization usually high energy electron beam is used to bombard a sample, and this technique shows us all other peaks of the destroying a molecule. And for the electrospray ionization involves the formation of ions in solution, typically by spraying or a sample dissolved in a solvent through the fine capillary. And this method usually shows less destroying the molecule than electron ionization.
Yeah, but okay, I was not asking this, but I was asking what mass analyzer did you use?
Oh.
What type of mass analyzer did you use?
Just
because you determined exact mass. For this purpose, you need high resolution mass spectrometer. So what type of high resolution mass spectrometer did you use?
I don't remember just.
Okay. Okay, I have other questions. So in your slides, I see the yields, but I don't see any standard deviations. So did you repeat your experiments? Did you repeat your synthesis?
Yes, we repeated our synthesis, and in the usually in the organic synthesis, we provide as yield the best result with the best impurity. Best purity, sorry.
Yeah, but this is not correct, really. So you need to find the average value and provide standard deviation. So if you choose the best result, this is not correct. Scientifically not correct. Yeah, because if you repeat several times, you can obtain different results. Yeah, and the other researchers can have problems to reproduce your results. Yeah, maybe your best experiment is the outlier. Outlier, it's just some accidental result. Yes, okay, so in your dissertation, you provide only the best result. Yes?
Yeah.
Okay. I have one. So another question. Can you open slide 15? Can you share the slides again? Because I closed them.
You said slide 15, yeah?
15, 15.
Mhm.
Okay, you write yield percents, not pure. What does it mean, not pure? What is not pure?
Yes, it's with electron withdrawing groups, we obtained our final compound and some of trace of phenol.
So these are impurities or what?
Yeah, it's impurity.
Okay. Okay, but when you had when you started your research, did you have any hypothesis?
Yes, because kind of research with aliphatic ethers with sulfur compounds and with nitro compounds were researched before we start this research in the laboratory of Professor Clive. And based on that knowledge, we tried to obtain good reaction conditions for this.
No, but what was your hypothesis? Can you formulate the hypothesis for your study?
Hmm. Oh, I can't.
Okay. Okay, so that's all from my side. Dear colleagues, do you have other questions?
Thank you.
Professor Fazilov, do you have questions? Okay. Okay, thank you. So we can move to the next step. And the floor is given to scientific supervisors. So the local scientific advisor, Dr. Moldir Akimjanovna Dusibayeva. So please, can you tell a few words about the PhD student and the research?
Thank you, Vlad Nurlanovich. Good day, dear colleagues. I would like to express my gratitude to the members of the Dissertation Council and the reviewers for reviewing Dinara's work. I hope that the decision will be positive, and let me read my review. Review scientific advisor for dissertation work Amankulova Dinara. The dissertation research conducted by Amankulova Dinara focuses on developing a new method for synthesizing methyl oxyphenols from 1,3 cyclohexanedione. Traditional methods for synthesizing methyl oxyphenols require harsh conditions and can pose environmental issues. The relevance of this research lies in its execution under mild conditions without catalysts using industrial available starting materials. The literature reviews in this dissertation examines various methods for synthesizing methyl oxyphenols. This section has been published in peer-reviewed journal. The experimental portion presents a universal method for synthesizing methyl oxyphenols from cost-effective and easily obtained starting materials. In this work, Amankulova Dinara developed convenient methods for preparation new methyl oxyphenols, which also serves as a foundation for synthesizing other types of compounds. She synthesized 80 previously undescribed new compounds. It's wrote noting that Amankulova Dinara completed this work during her doctoral studies, successfully finishing her planned work and achieving results of the scientific and practical interest. She has demonstrated herself to be a skilled and proactive experimenter with independent research capabilities. The works results have been sufficiently published in 3 publications, including 2 manuscripts in International Scientific Journal. The dissertation work titled Development of the Method for Non-Catalytic Systems of Meta-reloxyphenols from 1,3 cyclohexandione in content and volume fully meets the requirements for doctoral dissertation in the specialty AD 07105 Chemical Technology of Organic Substance. The author of the work, Amankulova Dinara Yerkenovna, is will prepared specialist for independent work and deserve to be awarded the required degree of doctoral philosophy in the specialty AD 07105 Chemical Technology of Organic Substance. Thank you for your attention.
Okay, thank you. Dear colleagues, do you have any comments to Dr. Dusibaeva? Any questions? So I have just one question about the input of the PhD student to the preparation of publications. Could you please comment on that a little bit, especially on the second one where she is not the first author in tetrahedron, I think. Okay, but probably, the second one, you are not among the co-authors, so probably, yeah, just about the first one. In molecules.
Can I speak in Russia? Она синтезировала 25 соединений, и 50 из них описала в данной статье.
Понятно. А статью, получается, кто писал первый вариант?
Первую статью, связанную с литобзором, писала наша исследовательская группа, то есть писала сама Динара, мы ее корректировали. А вторая статья, там чисто по обсуждению была работа, эта работа была по проекту профессора Клаева, и Динара там 70%, если не ошибаюсь, работ выполнена, то есть статья описана большей частью диссертационной работы.
Понятно, спасибо, thank you. Okay, if there are no other questions, then we can move to the review of the second of the foreign scientific advisor, Professor Clive, but he is not present. That's why the scientific secretary, Professor Tajibaeva, will read his report. Okay, so that may be
Dissertation assessment. The first part of the dissertation consists of a review of the literature on the formation of meta-aryloxyphenols by classical approaches and by more modern, especially metal-mediated reactions. This review in a modified form has been published as a 19-page article in a reference journal Molecules in this year. And this dissertation review explains the importance and application areas of meta-substitute phenols and the difficulties inherent in substitution of phenols at the meta position because of the ortho-para directing effect of oxygen. The review shows how these difficulties can be overcome. Numerous methods are described and the literature coverage is good. The review shows that many of the existing methods use harsh conditions. Dinara's research was on the development of a new and mild method for making meta-aryloxyphenols, and the second part of the dissertation explains the basis of the new approach and describes the types of spectroscopic information used to identify the structures of all the compounds. Assignments are made to most of the signals in both the infrared and nuclear magnetic resonance spectra. The route involves converting cyclohexane 1,3 and D1 into 2-chlorocyclohexane 2 and 1, displacing the chlorine substituent with the phenoxide and then introducing bromine at carbon 2. The last step calls for treatment of the resulting 2-bromo-3-aryloxy-cyclohexane 1 with DBU to effect aromatization. Overall, the method represents a mild alternative to the classical Ullmann reaction. In appropriate places, some mechanistic information is included, as is a discussion of experiments used to optimize the conditions for a number of the experiments. Then follows a section in which some suggestions are made as to how the method might be developed for industrial scale work. The next section is the normal description of the individual experiments with full instructions to enable an organic chemist to repeat the work. Finally, copies of NMR spectra are included as evidence not only of structure assignment but also of compound purity. Dinara gained experiments in modern standard experimental techniques of organic synthesis in running high-field NMR spectra and NMR spectra and interpreting the results. Her work here has been published in a referred journal, Tetrahedron, in 2023. Yours sincerely, Dr. Professor Cliff, Professor of Chemistry Cliff.
Okay, thank you very much. Dear colleagues, any questions to Scientific Secretary? Okay, if not, then let's go ahead, and then the floor is given to the first official reviewer, Dr. Justin Moore from the University of Illinois, United States of America. Okay, so Dr. Moore, you don't need to read everything, but the most important things, please mention. So we will share the screen with your review so that everybody can see the report. Thank you.
Видно, да?
No, нет, не видно.
Не видно? Тут. Dr. Lynch, can you show?
Okay.
Just
Okay, can you see the report? Okay, Dr. Moore, so the screen is yours. I'm sorry, we cannot hear you. The microphone, probably some problem.
Can you hear me now?
Yes, great.
It's working? Oh, okay. Switch the microphone. All right. Good day, everyone. Thank you for allowing me to participate. It's my first one of these international reviews, so something new for me. To the points of the review, I thought the dissertation was very well written and described the chemistry very nicely, as kind of mentioned by others so far. The literature review is quite thorough and deals with many of the alternative methods, including like the catalytic ones, as mentioned, and draws some nice analogies as to why the present method is particularly useful and orthogonal to some of the existing methods. So I found the characterization techniques for all of the compounds produced to be in accord with the typical methods for determining structure and purity for organic synthesis. The comments from the question and answer period notwithstanding, was consistent with what I would expect to see for compounds in this field to establish purity and yields. The two publications are very nice. The review article dealing with the alternative methods is very useful for contextualizing the research within the greater field, and then the tetrahedron article is more of an experimental paper, which gives lots of details on the specific method used and all of the characterization techniques for the new compounds that are synthesized. So overall, I had a positive view of the work done and the thesis as a whole. Any other parts that I should discuss in detail here? Again, this is my first time as a reviewer of in this format, so.
It would be nice if you comment these provisions, this
yes.
section number 7, yeah? So whether they are proven or not.
Yes,
give any comments on them.
Yes, I thought all the provisions were addressed sufficiently, providing the objectives of the thesis clearly defined in the 3 provisions, and I thought each of those was met. Each method has the methods have some limitations, but I think the limitations were adequately discussed in the thesis to again provide context in the greater field of synthesis. So yeah, I thought all 3 provisions were adequately addressed.
Okay, do you have any comments to the dissertation which should be revised or whatever?
No, I think that there were some minor things of structure drawing things that are maybe specific to the way I like things drawn, but I think everything was quite acceptable. I was quite impressed. I thought the writing in the thesis was very excellent. So I was quite pleased with the readability of the thesis.
Okay, thank you. So, but I have several questions to you. Maybe you can comment. So when I ask the questions about the mean values and standard deviations, and Dinara responded then that they selected the best results. Is it
Yeah, this is quite
that
common practice in synthesis. I think it's becoming somewhat less common. In my own research laboratory, we will report at least 2 results for each experiment that we describe, and then we report an average value for those 2 results, and then in the data report the exact results for the 2 repetitions, 2 or 3 repetitions, sometimes 3. But this is not so common within the field of synthesis. I would say, yeah. So there is some assumption that we are reporting reproducible yields, but that is usually not explicitly included in publications in the synthesis field.
Okay, thank you. And one last question is about these purities. So because NMR, as I told already, it's not suitable to analyze the mixtures of compounds, but so that's why it would be nice to see some chromatograms or maybe mass spectra to check the purity. What do you think about that?
The compounds are purified by flash column chromatography and then analyzed by NMR, as I would understand it. That's the standard practice in the synthetic field. And then so NMR would be used only after that on purified samples to establish their purity, and the conventional wisdom around NMR spectroscopy is that it's sufficient to maybe establish up to 95% purity before sensitivity becomes a limiting factor. It's certainly true that NMR can be difficult for measuring mixtures of compounds, although if they're well resolved in the NMR spectra, then you can determine percent compositions if the identities of the components of the mixture are known. In my reading of the thesis and looking at the few of the NMR spectra, it seemed that these compounds were sufficiently pure by NMR for certainly for structure determination, and then also for establishing purity within some reason. Certainly, HPLC or GC is more sensitive, although there are some limitations to those methods depending on the exact molecules. I would think HPLC would be certainly suitable for these compounds. They're likely UV active. GC may be limited. These are approaching the mass where GC is not going to be useful any longer. HPLC still has some limitations regarding relative UV activity of different components, which is perhaps not known, and has some limitations in determining the identity of the impurities, which maybe is also not known. Could be done by preparative HPLC and then analyzing the different components, but is sometimes done in organic synthesis, maybe less commonly. Usually in the fields, NMR purity is sufficient for publication in all of the major synthetic chemistry journals. Mass spectrometry is required for most journals for establishing exact mass, although usually only the high resolution data is required and no discussion of fragmentation is required unless in special cases where molecular ion cannot be observed directly. To my knowledge, no journals in the synthetic field utilize mass spectrometry for establishing purity. So that would defer to either NMR most typically, and then maybe less typically, maybe more in biological applications, you would rely on HPLC data. And then sometimes elemental analysis, although elemental analysis has some difficulties that are rather well documented in the field, and some journals have begun to remove elemental analysis even as a possible alternative to established purity. So it is predominantly NMR within the field of synthesis, to my knowledge.
Okay, thank you very much. Okay, dear colleagues, do you have any other questions to the reviewer? Okay, so your recommendation is to award the degree, yes?
Yes.
Okay. Okay, thank you very much. If there are no questions, then thank you again, and the screen is given to the. So if you have no comments, actually, you have no comments, so the PhD student should not respond, because in your review I didn't find the comments. Yes, so that the PhD student should respond then. Okay, thank you. Thank you. So then the screen is given to the second official reviewer, Professor Seilkhanov from Kokshetau State University. So Turgen Muratovich, please, the screen is yours.
Thank you. I may demonstrate your presentation.
Yeah, you will do it by yourself, okay? Okay, very good, thank you.
Review on the official reviewer for the doctor philosophy, for the doctor philosophy program. Question 1. The dissertation correspond to the priority of the direction of the development of the science approved by the Higher Scientific and Technology Commission under the government of the Republic Kazakhstan indicated in the direction. Second, the work make a significant contribution to science and importance is well disclosed. Third, the self-reliance level is higher. I comment read there. Therefore, the work is justified. The content of this thesis reflect to the topic of the thesis reflect. The purpose of the objectives correspond to the topic of this correspond. Then all sections of the provisions of the thesis are logically interconnected, completely interconnected. I read. Then the new solution proposed by the author are resolved to the evaluation and comprise with the own known solution. This is a critical analysis in this work. Then scientific novelty principles. The scientific results completely new. Then the dissertation finding new, completely new. I think. Then the technical, technological, and economical or management decision are particularly new. 45-75% new. The validity of the main finding, all main conclusions are on the based on the scientific significant evidence. I read there. Then for the seventh questions for the seventh question for the provisions for the provisions for the first provisions proven, then is not trivial. Then it is news application level medium and proved in articles. In the articles published for the pretendent in the journal Molecules and the journal Tetrahedron. Then for the answer for the provision 2, the proven, then it is not trivial. The is the news, yes. The application level medium, and it is proven is the article, yes. In the for the provision 2, provide in the articles tetrahedrons and molecules. For answer for the provision 3, is the provision proven, then it is not trivial. The news, yes. Application medium, and the proven in articles for the 3 proven in the articles molecules and tetrahedrons. Read about this. Then the principles of the reliability and reliability of the source of the informants proved. I think that the chosen methodology is injust fit, yes. Then the result of the thesis are obtained using modern method scientific research. I read the think that the work used modern methods scientific research such as mass spectrometry, ER spectrometry, NMR spectrometry. Yes. The answer for the question theoretical, the work have theoretical and practical confirmed. I read. I'm write this about this work have yes have theoretical conclusion and important statement confirmed for the practical. For the answer for importance the results obtained in the work, the obtained meta-aryloxyphenols, the characteristic and indicates are confirmed by the references to relevant and reliable scientific literature. The question for the question answer for the question 885, the list reference used include 128 titles. This is quite enough for the prepare literature review. Practical value principle. The thesis has theoretical value. Yes. The thesis practical importance. Yes. And the for the practical suggested news, the work the completely news, and the 10th quality writing of the design. I think the quality of academic dissertation writing is higher. As a note, I believe that the four meta-aryloxyphenols not previously described in the literature, the mass spectra and EI spectra could be present in the appendix. Before this answer, I know show about the mass spectra and the why the mass spectra not present in our work. Thank you for the attention, and I think to await the degree of Doctor of Philosophy in the education program Chemical Technology of Organic Substance Amankulova Dinara Irkinovna on the topics development of the method of for non-catalytic synthesis of meta-reloxy from 1,3-cyclohexane diones. Thank you for attention.
Okay, thank you very much, Professor Seilkhanov. Dinara, could you please respond to the comment of Professor Seilkhanov?
Yes, first of all, thank you for this good review. And as Professor Seilkhanov noticed, I already answered for this question. It's because of size of my dissertation work. And in addition, in the paper, in the tetrahedron journal, we didn't include mass and the IR spectra, so I decided to not include here too.
Thank you.
Thank you.
Okay, thank you. Dear colleagues, do you have questions to the second official reviewer? Okay, if not, then we should go ahead. So, Turgen Muratic, are you satisfied with the answer of Dinara?
Yes, I am satisfied for the answer of Dinara.
Okay, thank you. Okay, so dear colleagues, so now the next step of our defense is the discussion. So now please comment on the correspondence of the dissertation to the principles of independence, internal unity, scientific novelty, reliability, and practical value. If you see some errors in the dissertation, please let us know during your speech. Yeah, so please do not tell how you will vote. Yeah, because our poll will be secret. Yeah, so we should keep this during our speeches, during the discussion. Okay, so please raise your hand if you want to speak. Okay, Professor Buketbayev, please.
I think today we listen very interesting dissertation because, for my opinion, synthesizer have to know organic molecules. It means researcher have to be very sensitive to organic molecules and have to know every carbon atoms electronic density, and that density show him to Dinara the way how to synthesize the final substances. And I would like to underline, by the way, she has synthesized 54. It's I read in the dissertation 54 new substances, and even more. She identified all that compounds using very wide number of physical chemical approaches, methods, and I am sure that in my chemical department we very much need such kind of expert in the organic synthesis field like Dinara. So thank you very much, and of course I will be agree with official reviewers.
Okay, thank you. Okay, dear colleagues, who else wants to speak? We are particularly interested in the opinions of the temporary members of the council, which were invited to as experts in this field. Okay, so please, temporary members, your opinion is very important for us.
Төлеген, сен бетіңді көрсетші, сенің тек қана басыңды көріп тұрмыз. Төлеген. Иә, солай, соны көрсетші, басыңды шетін көріп отырмыз.
Okay, so Dr. Ospanov, do you want to speak? Just you ask some questions, and your opinion would be valuable for us.
Yes, thank you, Dr. Kenyatta. Because this work is interesting, and the synthesis always not easy, and as you said, it's they used NMR for identify the compounds mainly, and I think in my opinion it's more important than math or other equipments or other instruments, and I think she did good job, and I think she deserves to award this Doctor of Philosophy. Thank you.
Okay, thank you. Dr. Rafikova.
Yes, I agree with all reviewers and colleagues. Dinara did very huge work, but as my suggestions, I hope she will improve this research, find new ways of more short ways to synthesize all these compounds, and she can improve methods for synthesizing large scale products to be able to use in industry to have more economical effect. Thank you very much, Dinara. Good luck.
Okay, thank you. Dr. Kumarswamy Reddy, you asked a lot of questions.
Yeah. So thank you, Professor. So Dinara, first of all, congratulations to you. I completely agree with the reviewers. So the comments was very good, and I really appreciate her research. And in organic synthesis, the approach was very good. What she found, the finding synthetic route was efficient, and yeah. So I really, enjoyed our thesis, and the way of writing her thesis was excellent. Yes, thank you. And best of luck for the Dinara.
Okay, thank you.
I really agree to award this set of her award of her degree, PhD degree.
Okay, thank you. Professor Fazilov, can you tell a few words, maybe, может, на русском или казахша?
Рахмет. Уважаемый председатель, уважаемые члены диссертационного совета, обсуждаемая сегодня работа Аманкуловой Динары Еркиновны мне тоже очень понравилась. Соискателям предлагается новый удобный метод получения метаарелоксии фенолов из 1,3-циклогександиона. Синтез этих соединений всегда представлял определенные трудности для органиков-синтетиков. Это из-за стерических факторов, электронных факторов и других особенностей их строения. Вот органики-синтетики очень хорошо знают, что каждый этап синтеза этих соединений требует от соискателя, от молодого специалиста очень высокой квалификации, скрупулезности, в особенности при выделении и очистке целевых продуктов. Поэтому я считаю, что соискатель как научный исследователь состоялся, и поддерживаю ее и предлагаю голосовать за присуждение ей искомой ступени. Спасибо.
Спасибо, thank you. Okay. Does anybody else wants to speak? Okay, so I will tell a few words. We listen to the defense, and I see that the work is very big, so very important and novel. Yeah, a lot of compounds were synthesized. A lot of experimental results were obtained, which is very good, which I like, especially this mass spectrometry data. Yeah, however, I think that there are some issues with the dissertation. First of all, so in the experimental section, so Dinara should explain how the experiments were repeated. Yes, and if these results represent the best results, yes, so it should be clearly stated. Because for other researchers who will be interested to reproduce these results, or maybe to do the same synthesis, to synthesize these compounds, so they will expect these values which you report in the dissertation, but maybe some of them will not be able to achieve these results. Yeah, because they will think that maybe these are the average values or whatever. Yeah, so at least you should mention that in the dissertation. Second thing is that, okay, mass spectrometry data, so you provide exact masses which are used to determine the molecular formula of the molecular ions in the dissertation, which is very good generally. So I checked the instruments which we use, so you have the names of these instruments in the dissertation. Yeah, however, I don't understand why you use the word like mass spectroscopy. So this is not mass spectroscopy. Such method does not exist nowadays. This method is called mass spectrometry. Yeah, and experts in mass spectrometry, they don't like when somebody call it mass spectroscopy, because it does not study the reaction with light. So there is no light in the instrument. Yeah, so that's why it's just a measurement of mass spectra. Okay, there are also I don't like the provisions which you provide. So they can be improved really to better represent the results. Because, for example, the third one, it is just description of the method which was known before the experiments. This is what you wanted. So, but this is not something which you can prove experimentally. Yeah, so it was initially the method without using the heavy metals or ligands. Yeah, so this is not some conclusion or proven hypothesis in your work, because in the rules for the defense approved by the ministry, there is a definition for provision. So it should be the proven hypothesis or conclusions and other being this new knowledge, let's say. Yeah, okay, this is some knowledge, but this is not really the best thing in your work, because you did some experiments and you could really show the optimal parameters, etc., which you established during the experiment. Okay, so regarding the purity, there is a big discussion. So in my opinion, so nowadays the HPLC could be really useful to prove that the structure is okay. Okay, mass spectrometry can also be used. So from the mass spectra, you can generally see, especially from electrospray ionization, because electrospray ionization gives only molecular ions. So if you see, for example, 5 ions on the mass spectrum, that means that you have 5 compounds in your sample. Yeah, so that's why that's very important for the estimation of the purity. So if you have this data, it's not difficult to check. Yeah, because you have mass spectra, they are recorded on the instrument, on the computer, so you can easily check them. So we could check them if you provide them in the thesis, but somehow you have only NMR spectra, which are also important, but at least for mass spectrometry, you can write something in the thesis So you can write, for example, that no other peaks were on the mass spectrum, so there was only one major peak, something like that, but it was not, I don't see it in the thesis. Yeah, so generally you, as Dr. Moore said, that the methods which you use to purify are okay, but sometimes you can have some isomers, but isomers are not separated by mass spectrometry. Yeah, for this purpose, you should use some kind of chromatography. Yeah, because mass spectrometry separate by mass, so and you will have the same mass. So actually, mass spectrometry used only to determine the molecular formula. Yeah, but from the electron impact ionization, you can have the fragments. And generally, these results could be helpful and compared with NMR. So if there is any contradiction, you could easily state that. Because you see the fragments, and your molecules are not that big. Yeah, and you should have a lot of fragments. Yeah, and generally, at least it will be another confirmation of your results. Yeah, but you know, your results are published in good journals, which are, so tetrahedron is the third quartile in organic chemistry on the last year. Yeah, and we have also the molecules, which is second quartile. Yeah, which are good journals, and they follow the rules. Okay, so that was my opinion about the dissertation, and I hope that colleagues will, this opinion will be helpful for the decision during the voting. So, and now I want to give the word to Dinara Amankulova, to our PhD candidate. Yeah, and this is like the last word before the secret poll.
Thank you for all members of committee for participating in this meeting, reviewing my work, and the good, thoughtful feedbacks. Also, I would like to express my appreciation to my scientific supervisors and all staff of Kazakh National University and the University of Alberta. Thank you.
Okay, thank you. Okay, so dear colleagues, so now we could move to the secret poll that will be conducted here in Zoom. Yeah, so all members of the council and official reviewers must vote. So for other defense participants, we have the break, and you will be moved to the waiting room. Okay, so don't disconnect, I will move you to the waiting room. And then after we finalize the secret poll, we will invite you back. So I will connect you, okay? Is it clear? Okay. Okay, so now we have only the members of the dissertation council, and I will connect from my another account. Just a second. Because I cannot vote from the main account, because I will start the secret poll from this account. I can only vote from another one. Okay, this is also me. Okay, now so now we have everybody. So I will start on your screen, right in Zoom, you will see the window with the poll. Yeah, so now I will launch it. Yeah, so please vote for one of the decisions. Кто-то не проголосовал. Серик Драхметович, вы проголосовали? Okay. So now we have all votes. So I need some time to save the screenshot. Okay, so I finalized the poll. Okay, so now I can invite PhD student and the supervisor. Okay, so everybody is back. So now we are ready to announce the results of the secret poll for the decision. So I will share the screen, just a second. So can you see the results? So are there any questions to the results? Okay, if there are no questions, then I will close it. So then I can announce the decision of the dissertation council. Yes, so based on the defense and the results of the secret poll, our dissertation council at Al-Farabi Kazakh National University awards the PhD degree to Dinara Amankulova on the educational program Chemical Technology of Organic Substances. So my congratulations to Dinara, Dr. Amankulova, now, yeah, and her supervisor, Dr. Dusibayeva, and all members of the dissertation council. So many thanks for your active participation, and I wish you success in your research. Thank you very much. And now I finalize the defense and I close the broadcasting. Thank you and bye.
Congratulations.
Наши поздравления.
Congratulations. Bye.
Спасибо.